Check this out. We've got something really fun today. This is so amazing, math. Oh man, again? 1.4, using limits to find tangents. If we have P and Q represent any point on a curve, the slope between them can be found using our slope formula. Now, if we want to find the slope of a tangent, like in the first section we did, we're going to slide Q infinitely close to P. Now we'll make this our first point, so A here, whatever our x value is at point A, that will be our x1. And the function at A, that will be y1. And this point here that's getting closer and closer to P, this will be x2, y2. So down here, we're going to take our y2, which is f of x, and minus y1, which is f at A, and then x2 minus x1, which is x minus A. And then we're going to do a limit. So we're going to say the limit of all of this as x approaches A is going to be the slope of the tangent. And this is going to be called Formula 1. Find the slope of the tangent at the point 1, 1 for the function y equals x squared using Formula 1. So we would have the limit as x approaches 1. That would be the x value of the coordinate we're interested in. So A equals 1 here. Next, we have our equation here. We don't have it in function notation, but it would be f of x equals x squared in function notation. So f of x is just x squared. So I can put that in our formula. F at A would be, in this case, f at 1, which is 1 squared, which is 1. So 1 there, and x minus 1 in the denominator. Now I can do some algebra. Remove this problem here. I can't let x approach 1 yet, or I'll have 0 in the denominator. But I can factor the numerator to be x plus 1, x minus 1. And then I can cancel these matching factors. And now it's safe to let x approach 1. So I will not write limit anymore. I'll just use 1. And 1 plus 1 is 2. So the slope of the tangent at this point is 2. Find the equation of the tangent when x equals 2 for the function y equals 2x squared plus 4x minus 1. Now this is a bit more than the last question. The last question just asked for the slope. This one's asking for the equation. But we still start off finding the slope here. So the limit as x approaches 2. So this time our a value is 2. F of x, that would be all of this stuff. So 2x squared plus 4x minus 1. Now we need f at a. So we can go find that separately, or we could find it in here. I'll find it separately. So f at a would be f at 2. That would be 2 squared plus 4, 2 minus 1. Okay. And this would be 8 plus 8 minus 1 is 15. So f at a is 15. And then in the denominator, we've got x minus a, which is 2. Now let's see what we can do. This looks like a good candidate to factor, so let's clean it up and see if we can factor it. The limit as x approaches 2, we've got a 2x squared plus 4x minus 16. Looks like there's a common 2 here that we can factor out. And then we can factor this quadratic. Notice I'm writing limit every time. So we've got, looks like x minus 2x plus 4. And that's good because we have an x minus 2 in the denominator, so now we can get rid of that. Now we don't have a denominator, so it's safe to let x approach 2. And it looks like 2 times 6 is 12. So the slope of the tangent is 12. Now let's go make the equation of the tangent line. Let's use slope point form because we have the slope now and we have a point here, 215. So slope point form is y minus y1 equals the slope times x minus x1. So our y is our variable minus the y1, which would be 15 in our case. The slope was 12. X is our variable, and x1 is the x value of this point we know, 2. And there is the equation of the tangent line. Now that would be 100%, that is an equation. There's nothing wrong with it. If the question did say, make the equation in slope y-intercept form, then we could do some algebra, rearrange this. So we could add 15 onto both sides here. So 12x minus 24 plus 15. So I distributed in the 12 and added the 15 on that side. Then I get y equals 12x minus 9, and that would be the same equation, just in slope y-intercept form. But don't think that you have to put it in this form. This is a perfectly good form, unless the question says otherwise. There's another way to find the slope. Again, we've got the same initial setup. We've got point P and point Q, and we're moving Q infinitely close to P to get the tangent. But this time, we're not going to use this other value here. We're going to use the distance between the two x values of P and Q will be h. And then we're going to say that that distance h is going to go to 0. So eventually this distance between here and here is going to go to 0. That would mean that this point still is A and f at A. And this point here is going to be A plus h and f at A plus h. So using the same slope formula we had before, this is how it would look, except the denominator will clean up a bit. So we have a here and minus a here, and so we can just clean that up, and this becomes our formula 2. Find the slope of the tangent at the point 1, 1 for the function y equals x squared using formula 2. This would be the exact same example as example 1, except we're going to use formula 2. So our a here is still equal to 1. We have the limit as h approaches 0. Our f of x is x squared. We need f of, and our a is 1, so we need f at 1 plus h, which will be 1 plus h squared. So we replace the x with 1 plus h. And we're going to need f at a, which is f at 1, which is just 1. Now that we have everything, let's put it in here. So we've got 1 plus h squared minus 1. And in the denominator, we just have an h. Okay, we're going to have to multiply this out, it looks like. So the limit as h approaches 0. 1 plus 2h plus h squared minus 1 all over h. Now first you can see that we can get rid of the 1's because we have 1 minus 1. Now I'll do this in 2 steps, but you could probably do it in 1 step. The limit as h approaches 0, 2h plus h squared over h. Now we can factor out an h from the numerator and cancel it out with an h in the denominator. So I'm just going to cancel one h out in all those terms. Then we would have a 2 plus 0, and that would just equal 2. And we know that's the answer we got before. Now there was another way we could do this. We put in a as 1 right at the beginning here, and that worked out fine. You see we got the answer, but what happens if we didn't? What happens if we had the limit as h goes to 0, and we just kept a as a for now, till the end? So then we'd have a plus h squared minus a squared instead. So instead of putting 1, we would have f at a, and for this one here, we would have f at a plus h, which is a plus h squared. Okay, and then in the denominator, we'd still have this h. So I didn't put a equals 1 in here yet. Let's see if we can still work this out. So the limit as h approaches 0. Let's expand that. A squared plus 2ah plus h squared minus a squared. And you see the same thing is happening here. The a squareds will cancel. A squared minus a squared will cancel. And then I'll just do it in the same step. One of these h's will cancel with this h in the denominator. So we would then have the limit as h approaches 0. What's left? 2a plus h. And so we can now let h go to 0, and we just get 2a. And now we can put in a is equal to 1, and we would get 2 times 1, which is 2. So it did work. We can put in the a value at the beginning, or we can put in the a value at the end. Find the equation of the tangent when x equals 2 for the function y equals x squared minus x minus 6 using formula 2. So here we would have the limit as h approaches 0, and a would be 2, so let's do f at 2 plus h minus f at 2 all over h. Now the first part, the limit as h approaches 0, doesn't change, and f at 2 plus h, so we need to replace x with 2 plus h, and this x with 2 plus h. All right, then we need f at 2, so I'll find f at 2 up here. We've got 2 squared minus 2 minus 6, and that will give us negative 4. So I'll put minus negative 4 here, and then all over h. Now I'll expand this out, so we've got the limit as h approaches 0 of 4 plus 4h plus h squared minus 2 minus h minus 6 plus 4 all over h. Now I can cancel a few things out here. How about the numbers? We've got 4 plus 4 is 8, and minus 2 minus 6 is negative 8, so those will all cancel. And we've got a 4h minus h, so that would be 3h. So I'll write that on the next line. The limit as h approaches 0 of 3h plus h squared all over h. And now I can cancel out the h in the denominator because it's a common term. So one of those will cancel out with one of those h's. Now I will have the limit as h approaches 0 of 3 plus h. And now it's safe to let h approach 0. And so that would be 3 plus 0, or just 3. It says find the equation of the tangent, and we just found the slope of the tangent. So now we need to go back and make the equation of the tangent with that slope. So y minus y1 is equal to m x minus x1. And we'll do y minus, what's our y value? I love this, negative 4. So we'll just do plus 4. The slope we just found was 3, and x minus 2. And that is the equation of our tangent line. Find the equation of the tangent when x equals negative 2 for the function y equals 1 over x. We've got a formula 2 here, so we're going to have the limit as h approaches 0 of 1 over negative 2 plus h minus 1 over negative 2 all over h. Now we probably don't like these fractions in the numerator, so let's get rid of them. First, we'll get rid of the negative and negative, so we'll just make that positive. Next, we need a common denominator, so this one has an h minus 2, so let's multiply this by h minus 2 over h minus 2. This one has a 2, so let's multiply this one by 2 and by 2. So we have the limit as h approaches 0. This would be 2 plus, and then distributing in the 1, just h minus 2. And then we have in the denominator here of the numerator, we've got 2 and h minus 2. And then in the denominator, this overall denominator here, just draw it a bit thicker because that's our overall one. Okay, and then there's an h down there. Now we see that 2 minus 2 will cancel out. So that's gone. And then we have the limit as h approaches 0 of h over 2h minus 2. Now we're dividing by this, so this is really h over 1. So when we dividing by a fraction, we can multiply by the reciprocal, so 1 over h. So this h anyways ends up down here. Now that's good because we can use that h to cancel out the h in the numerator. Just remember that when I cancel it out, it becomes 1 up here, not 0. It's a common mistake I see students doing. So I'm going to put a 1 right there, just so you remember it's not 0. Next, it's now safe to let h go to 0, because that's not going to give us a 0 in the denominator. So I'm going to get rid of this limit. I've got 1 over 2, 0 minus 2, and that gives me negative 1 over 4. So that's my slope, negative 1 over 4. Now let's see if that is an appropriate or realistic slope of a tangent. So I'm going to sketch this function this time, and if you had time, it would be a good idea to always do that. This is 1 over x, so that means that we've got a vertical asymptote at x equals 0, and we've got a horizontal asymptote at y equals 0. Then the graph follows this one along like this until it curves down, and then follows this one along here until it follows that horizontal asymptote. And we're doing the slope of the tangent when x equals negative 2, so that would be about here. And so if I was going to draw a tangent line, it would have a slope, a negative slope, and negative 1/4 would seem very realistic for that tangent line. Let's figure out the equation of that tangent line now. So we have y minus y1 equals mx minus x1. Y is our variable. y1 is the y value, so that would be this negative 1/2 we came up with. The slope is negative 1/4, and x minus negative 2 gives us this equation in slope point form. Find the equation of the tangent when x equals 6 for the function y equals the square root of x minus 2 using both formulas. First we'll do formula 1 here. We've got the limit as x approaches 6. That means we have f of x here, which is just our function, so root x minus 2, and then minus the square root of 6 minus 2. And in the denominator, we would have x minus 6. We've got some things we can simplify here. the limit is x minus x approaches 6. We've got the square root of x minus 2 minus. Now 6 minus 2 is 4, and the square root of 4 is 2. Okay, now we can't factor this, but we can multiply by the conjugate. So x, the square root of x minus 2 plus 2, top and bottom. So I'll put brackets around that and this, just so we know that's separate. And in the bottom, I'm not going to distribute these in, but in the top I am. So we've got the limit as x approaches 6, and root x minus 2 times root x minus 2 is just x minus 2. And then the middle term will cancel, and the last term will show up, and that would be minus 4. And then in the denominator here, we've got x minus 6, and this conjugate here. Okay, now in the numerator, we have essentially x minus 6, and in the denominator, we have an x minus 6. So those are going to cancel out with each other. So we'll just do that this step. Remember, in the numerator, we end up with 1, not 0. Now, it's safe to let x approach 6. So we have 1 over, and it's 6 minus 2 in the denominator. And we can do that. And this would be the square root of 4, which is 2 plus 2. So we get 1 over 4. Now, the equation we could do as y minus, and we use this point here, so that would be 2, and then 1/4, and x minus 6. So there is the equation of the tangent line. Now let's try using formula 2. So coming back up here, we've got the limit as h approaches 0. And this time we want the function 6 plus h minus 2. So the square root of 6 plus h minus 2. And f at 6 is 6 minus 2. So you can see the similarities here and here. This is going to be just h in the denominator. Now we've got the limit as h approaches 0. We can simplify this one. 6 minus 2 is just 4. So we've got 4 plus h, and then minus. This will equal 2 again. And this is over h. Now we can do a similar thing as we did over here, but this time the conjugate will look a bit different. Root 4 plus h plus 2, and in the denominator as well. And then we're going to multiply in the numerator, but not the denominator. So in the numerator we get 4 plus h minus 4. In the denominator we've got the h, and we've got this conjugate. And the 4 minus 4, they're going to cancel out. And I'll do it in one step this time, but the h that's left and this h will also cancel, and we'll be left with 1 in the numerator. So we will have the limit as h approaches 0, 1 over the square root of 4 plus h plus 2. Now we can let h approach 0, so we'll get 1 over root 4 plus 2, which is just 1 over 4. Now we are using the same point, so this will be the same equation that we come up with. Find the equation of the tangent when x equals -2 for the function y equals x over 3x plus 2. Let's use formula 1 and formula 2 to do this. So for formula 1 we have the limit as x approaches -2. first we want f of x, so that would be x over 3x plus 2. And then we want f at a. In this case, our a is negative 2. So I'm going to write it up here, f at negative 2, because I also need it over here. So negative 2 over 3 times negative 2 plus 2. And this will be negative 2 over negative 6 plus 2 is negative, so 1/2. Alright, so this will be minus 1/2, and all over x minus negative 2, so x plus 2. Then we've got this annoying situation happening again with fractions in our numerator, so let's get rid of those. So we'll multiply both of these by 2, and then we'll multiply both of these by 3x plus 2. So the limit as x approaches negative 2, let's multiply this by 2 top and bottom, and this by 3x plus 2 top and bottom. Let's clean it up. So in the numerator of the numerator, we have 2x minus 3x minus 2. It's distributed in that negative sign. And in the denominator of the numerator, I've got 2 and then a 3x plus 2. Then in the overall denominator, make this a bit darker, we've got x plus 2. Alright, let's clean this up a bit here. So we've got the limit as x approaches negative 2, and we've got negative x minus 2. Now that looks suspiciously like this one, except it has a negative. So I'm going to factor out the negative, and I'll be left with x plus 2. And no change for this. And here is my denominator, x plus 2. So I'm going to cancel those ones out. So this one and this one. And so I'll be left with a negative 1 in the numerator there. So the limit as x approaches negative 2 is negative 1 over 2, 3x plus 2. And now I can let x approach negative 2. So I'll have negative 1, I'll have 2, I'll have 3 times negative 2 plus 2. And then that will give me 1 over 2 times negative 6 plus 2 is negative 4. And negative will cancel, and I'll be left with 1 over 8. Now, it did want the equation of the tangent, so I'd be doing y minus, and the y value was 1/2, and the x value was negative 2. So y minus 1/2 equals the slope x minus negative 2 would be like this. So there's the equation in slope point form. Now let's try this question again using formula 2. So we have the limit as h approaches 0, and this is f at negative 2 plus h, and this is f at negative 2 all over h. So we have the limit as x approaches 0. Now this here is this function, but with negative 2 plus h replacing the x. So 3 negative 2 plus h plus 2. And minus 1/2, just like we had before. And all over h. Now, let's multiply this again before we go any farther. The limit as h approaches 0. I'm going to switch this around just because I like to lead with a positive term here. So h minus 2 instead of negative 2 plus h. And this one here, negative 6, 3h. So I'm going to write 3h here, and negative 6 plus 2 is minus 4. And then I've got a minus 1/2. Now I need to get rid of this fraction, so I'll multiply this one by 2, put brackets around this so I know it's going to be distributed in, and on this side a 3h minus 4, top and bottom. Alright, now we have the limit as h approaches 0, and this one will be 2h minus 4 minus 3h plus 4. That's a good sign because that's going to cancel out there. Here we have 2 and 3h minus 4. I'm leaving this factored. And in the very overall denominator, the very overall, would be the h. I'm going to clean up this top here. So I've got the limit as h approaches 0, and this is the h's cancels, the 4's cancel, and I'm just left with negative h up here, and that's perfect because that will cancel out with this h here. Okay, and so that one and that one. And then the limit as h approaches 0, we've got negative 1 over 2 times 3h minus 4. And now it's safe to let h go to 0. So we have negative 1 over 2 times negative 4. Negatives cancel, and we end up with the same slope as with the other formula, 1 over 8. Find the equation of the tangent when x equals 0, 1, and 2 for the function y equals x cubed. Now, because they want us to do all three of these values, we don't want to put in these values until the very end. We want to get a general equation and use that with all three of these values. Let's see how that might work. So for the formula 1 here, we have the limit as x approaches a, and I'm not going to put a in here, I'm just going to use a. Next we have f of x, so that would be x cubed, and we have minus f at a, so that would be a cubed. And this is x over a. We need to factor this difference of perfect cubes, so we have the limit as x approaches a, and we do SOAP, so same sign, and then opposite sign, and then always positive to factor that. And it's all over x minus a. And then you can see we can get rid of those two factors. And then we can let our x approach a. So everywhere where we see an x, we're going to replace it with a. So we'd have a squared plus a times a again plus a squared. And you can see that this would be a squared plus a squared plus a squared, or 3a squared. And now we could actually use 0 in here, or 1, or 2, and get 3 different slopes, instead of doing this whole process 3 times. Let's try formula 2. We have the limit as h approaches 0, and our function here is a plus h cubed. And we need to minus a cubed all over h. We need to expand this out, and we'll probably use the binomial theorem for that so that we don't have to do any work. So this one would be 1a cubed plus 3a squared h plus 3a h squared plus h cubed. And then the minus 3a cubed all over h. And you can see that our a cubes will cancel out here and here. And also I'll do it in the same step. 1h from the numerator will cancel out with 1h in the denominator. If that is too much happening in one step, then split that into 2 steps. Then we have the limit as h approaches 0 of 3a squared plus 3ah plus h squared. And when we let h approach 0, this term and this term disappear, and all we're left with is 3a squared. Now let's actually find the equation of the tangents at 0, 1, and 2. So when x equals 0, then our slope is also 0. And the point on the graph y equals x cubed would be 0, 0. So the equation of the tangent is actually just y equals 0, a straight horizontal line. So if you think about that graphically, that's pretty interesting. We have a cubic, comes up and goes up there, and the tangent line would be at the origin here, it would be passing straight through here. Okay, when x is equal to 1, then our slope would be 3. Just put 1 in there, 1 squared times 3 is 3. And when from the equation, when x is 1, we get 1 cubed is 1. So the point that it's going through is 1, 1. So we'd have y minus 1 equals 3x minus 1. And that would be the equation of the tangent that passes through this point, 1, 1. And last one is when x equals 2. That would be 2 squared is 4 times 3 is 12. So the slope would be 12. And the point, 2 cubed is 8. So the point it's passing through is 2, 8. So the equation of this tangent is y minus 8 is equal to 12, x minus 2. Find the slope of the tangent at any point x for the function y equals 1 over x. So we have the limit as h approaches 0, and we're going to use any point x, so we'll say 1 over x plus h minus 1 over x. This is all over h. Again, we want to get rid of these fractions in our numerator, so the limit as x approaches 0, multiply this one by x and x, put brackets around that because we need to distribute it in. This one is x plus h over x plus h. So we have x minus h, and we got x and x plus h here, and then under it all is our h. Now these x's obviously cancel out, so they're gone, and this h and this h will cancel, leaving us with negative 1 in the numerator. This will give us the limit as h approaches 0, negative 1 over x times x plus h. And now we can let h go to 0, and all that's left is negative 1 over x squared. So this is the slope of the tangent at any point x. We do have a problem here, and it looks like we have a non-permissible value, so we'll say that x cannot equal 0. But this makes sense because our original equation here had the same non-permissible value. We couldn't possibly have a tangent where the graph doesn't exist. Hopefully now you can use formula 1 or 2 to determine the slope of a tangent, and you can determine the equation of a tangent line at any specific point or a general point x. Here's some questions from the textbook. Give them a try. See if you know what you're doing.